Good morning, everyone. Myself, Dr. Ramesh Srivastava. I'm professor in CSE department, SIIT. So today we'll be starting the lecture 3 of module 2, and we'll be continuing the concepts of paging. So here we are having a free frame list maintained by the operating system. And suppose a new process comes in which we have got 4 pages. So these pages will be allocated frames from this free frame list. Like here, page 0 has been allotted frame 14, page 1 has been allotted frame 13, and so on. So operating system is maintains this free frame list for allocation of these frames to the new processes. Continuous memory location, also known as MVT, multiprogramming with a variable number of tasks, is the memory management technique in which each job gets just the amount of memory it needs. That is, the partitioning of the memory is dynamic and changes as jobs enter and leave the system. So we have already previously seen that there exists both external and internal fragmentation in this kind of scheme. And paging, also known as MFT, multiprogramming with a fixed number of tasks, is one of the old memory management techniques in which the memory is partitioned into fixed size partitions, and each job is assigned to a partition. The memory assigned to a partition does not change. Disadvantage is here only internal fragmentation exists. There is no external fragmentation. Now, what can be the maximum internal fragmentation which can exist? So it will be page size minus 1 byte. For example, if the process size is 1025 bytes and the page size is 1024 bytes, then we have to allocate 2 pages for this particular process. And the first page will be utilizing all the 1024 bytes, but the second page will be utilizing only 1 byte out of this 1024 byte. That is, 1023 bytes will be there as a external, as an internal fragmentation in the second page. Now let us look at this some example or numerical. If page table entry is 4 byte long and frame size is 4 KB, then how much memory can be addressed? So now we know that the logical address consists of 2 fields. One is the page number and another is the offset of the page. So here we have given the frame size to be equal to 4 KB. It simply means that the page size is also 4 KB and the page table entry is 4 bytes long. Okay. So if entry is 4 bytes, then how many entries can be there present in the page table? So if entry is 4 bytes, then frame can be stored in the 32 bits, right? That is, 2 to the power 32 frames can be there with each of size 4 KB. That is, the total memory which can be addressed is 2 to the power 32 into 4 KB. That is 2 to the power 32, and we can write 4 KB as 2 to the power 2 into 2 to the power 10. That makes 2 to the power 44, and we can write it 2 to the power 4 into 2 to the power 40 bytes. That is nothing but 2 to the power 4 terabytes. So 16 terabyte of memory can be addressed if this kind of scenario is there. So one thing you have to remember is 1 KB is equal to 2 to the power 10, 1 MB is represented by 2 to the power 20, 1 GB is 2 to the power 30, and 1 TB is 2 to the power 40. Okay. So now the hardware support which is required for implementing this paging scheme is page table is kept in the main memory. Each process has got its own individual page table. Page table base register points to the base of the page table. Whenever the process changes and hence the page table changes, then we just have to change the PTBR value, that is page table base value, which will now point to the new page table address. Okay. Again, the loading of this or changing of this PTBR value is done in the privilege mode, and it is done by the operating system. So user is not allowed to change its value. Let each page table entry takes 4 bytes to store a frame number. PTBR is pointing to address 100. So what will happen? Each page table entry is requiring 4 bytes, and PTBR, that is page table base, is pointing to the 100th address. So it means that at 100th address, we have written the page number 0 frame number, right? The page 0 is there in the frame 40. So first entry is this. Second entry must be 4 bytes away from this 100. That is at 104, the second entry will be done. At 108, the third entry will be done, and so on. So now suppose we want to search page number 7. Then simple calculation will be, since each page table entry is requiring 4 bytes, and we want to go to the page number 7, so 7 into 4 plus the page table base registers, we just added 100, so we are getting 128. So it means page number 7 must be present at 128 address in this page table. So we can see here the address is 128 and the page number is 7. So this is how we can calculate the page number is at which memory address. Now, hardware support for implementation of the paging scheme. So page table length register indicates the size of the page table, and the two memory access problem can be solved by use of a special fast lookup hardware cache called associative memory or translation look aside buffers. Now, first of all, let us understand that what is the problem which we face if we are using the paging scheme. So previously, when we were not using paging scheme, then in that case, whenever the logical address is generated, then for executing that instruction, we require to access the memory, the main memory, only once. But now, when we have introduced the paging scheme, then what happened? Since this page table is also present in the memory, main memory, right? So first of all, the logical address which is generated in the paging scheme is in the form of page number and offset within that page. So this page number had to be searched in the page table, which is present in the main memory. So one memory access is required for accessing the page table so that we can get the frame number. Then this frame number is added to the offset to get the physical address. So the physical address, when we execute the physical address, then again we are accessing the memory. So it means when the paging scheme is introduced, then we have to access memory 2 times as compared to the previous scheme in which we have to access the memory only once. So it simply means that if the program executes within 5 minutes or in 5 minutes in the first scheme, then it will take 10 minutes to execute in the second scheme, since we are using the paging scheme. So for reducing that time, we make use of special type of memory known as TLB, that is translation look aside buffer. It is an associative memory which is very fast as compared to the main memory, and the parallel searches are possible in this associative memory. So this is a scheme in which we introduce TLB. So what happens? CPU is generating the logical address in the form of page number and offset. We are looking this page in the page table. Fine. Now, when we introduce TLB, then we store frequently used pages in this TLB. So first of all, this page number is searched into this TLB. If we find our page number here, so we can get the frame number from TLB itself, and we say that the TLB is hit. Okay. But if in case we don't find our page in this TLB, then we go to the page table and find the corresponding frame from this page table. Then we add this frame number or the physical address of the frame to the offset to get the actual physical address. So one time we are accessing the memory here while accessing this page table, and second time when we execute the instruction. So 2 memory access are required for each logical address to be executed. Fine. Now, this TLB is keeping the frequently used pages. It works on the principle of locality of reference. Like example, suppose I am presently executing page number 2 of my process. Now let us say there are 10 pages. So what is the probability that after page number 2, what page I will be executing? It will be obviously 3, until unless we call some subroutine or something like that. So the probability is higher that whatever page we are executing, the next page will be frequently accessed. So what we do, we keep, suppose I've got, let us say, 3 entries in this TLB. Then what I will do, whenever when I'm accessing page number 2, then I will keep the entries of 2, 3, and 4, all 3 in this TLB. So the chances of finding the page number which this logical address is generating is that we will find that entry in the TLB itself. So we can increase our TLB hit ratio. Okay. In case we miss the page or we are not finding the page in this TLB miss. Okay. Now, next term is hit ratio. The percentage of time the particular page is found in the TLB is known as hit ratio. So 80% hit ratio means that we have found the desired page number in the TLB 80% of the time. And miss ratio means the percentage of time the page is not found in the TLB. And we have to refer to the page table for that particular page. Now, suppose for example, to search the entry in the TLB, it requires only 29 seconds. And while if we access the memory, then it is 100 nanoseconds. So what is the effective memory access time? The hit ratio is 80%. Now, please note that without paging scheme, effective memory access time was 100 nanoseconds. When we were using the paging scheme, then the total effective memory access time is 200 nanoseconds because we are requiring two memory access, one for the page table, another for the actual physical memory instruction. Now, effective memory access time with TLB with 80% hit ratio will be total time required when the page is found in TLB is 100 nanoseconds for the actual data access plus 20 nanoseconds for the TLB search. That is 120 nanoseconds. Right? So 80% of the time required will be 120 nanoseconds. And so 20% of the time, we are not finding our entry into the TLB. So what will be the total time there? 100 nanosecond for the actual data access, 20 nanosecond for the TLB search, and then when we have found that there is no entry of our page. So we will go to the page table. So 100 nanosecond for the page table again. So total 220 nanoseconds will be required, 20% of the time. So 0.80 into 120 plus 0.20 into 220 gives us 140 nanoseconds. It means that 40% slowdown as compared to 100% slowdown when TLB is not used. When we are not using TLB, then the effective memory access time was 200 nanoseconds. So we are getting somewhere in between 100 and 200. We can never achieve 100, but we will try to be as close as possible to the 100 nanoseconds using this TLB and increasing the hit ratio of this TLB. If the hit ratio is 98%, then in that case, we are getting the effective memory access time to be 122 nanoseconds. That is 22% slowdown as compared to 100% slowdown when TLB was not used. Okay. So now next, for memory protection, we make use of valid, invalid bit. Valid bit indicates that the associated page is in the process logical address space and is thus a legal page, whereas invalid indicates that the page is not in the process logical address space. Suppose logical address space is 14-bit address space, that is 2 to the power 14. It means 0 to 16383 addresses can be addressed in this logical address space. We have a program that can use only addresses from 0 to 10468. Okay. Now, given a page size of 2 KB. So how many pages we will have to allocate to this particular program, which is of size 10,468. So 5 pages will have a size 10 KB because 2 KB into 5. So 10 into 1024, it gives us 10240. So now 10240 is less than this 10468. So it means we have to allocate 6 page also to this particular program. Now, 6 pages addresses will be ranging from the 6th page address will be ranging from 10 to 40 to 12 to 87. That is the addresses from 10468 to 12 to 87 will be internal fragmented in this page, right? Because the program size is 10468. So in the 6th page, we will be using the memory only up till 10468, whereas the 6th page last address is 12 to 87. So from 10468 to 12 to 87, there will be our program will not be using that particular memory. So it will be the internal fragmentation. Now, as per logical address space of 14 bits and page size of 2 KB, we have logical address of P and D. Okay, how we calculate this 3 and 11? So page size is 2 KB. So it means we can write it as 2 into 2 to the power 10. That is 2 to the power 11. That is the offset is consisting of 11 bits. Total logical address space is 14 bits. So 14 minus 11, that is 3 bits will be there for the page number. Fine. So page number will be total number of bits in the page number is 3. So by 0 and 1, how many combinations we can make? From 0, 0, 0 to 111, that is 8. And how we can calculate it directly? 2 to the power 3, that is 8 pages. So 8 pages of size 2 KB can be there in this logical address space. So total of 8 into 2, that is 16 KB of logical address space is present in this 14-bit address, logical address space. Okay, so we can calculate it like this also. Okay, so as I mentioned, the valid invalid bit. Here we can see that in this program we have got only pages from 0 to 5, that is 6 pages are there. So in the page table, let us say our page table, our logical address space is having 8 frames or 8 pages, entry of 8 pages, and our program is having only 6 pages. So what we will do for first 6 pages, that is from 0 to 5, we will write V, that is valid bit. It means these pages are legal pages of this particular program, whereas we have written I in page number 6 and 7 entry. So it means these entries are invalid for this particular program or for this particular page table. That is, the process is not using this 6th and 7th entry. It is invalid. Okay. So here we can see that our 8 bytes are unnecessary wasted. If we consider that each entry of a page table is requiring 4 bytes, so it means last 2, that is page number 6 and 7, 2 entries are wasted. That is 8 bytes are wasted. But this is just an example of 8 pages. Normally, the size of the page table is very large, and in that case, let us say our program is using only 10 pages or 20 pages out of, let us say, 2048 entries. So remaining entries will be invalid, and it will be wasting per entry will be wasted. Each entry will be wasting 4 bytes, and each process has got its own page table. So lot of memory is wasted unnecessarily. So what we can make use of is another hardware which is known as page table length register, which indicates the length of this table. So till length of the table only we will be constructing the table, and remaining entries we will simply not construct. So it will save a lot of space. So we can do like that. Now, in sharing, how we can use this sharing concept in the paging. Let us say I've got 3 programs running, and all the 3 programs are using MS Word. That is, they are typing some letters, let us say. So the letters will be different, but the code, which is MS Word, the editor itself is a reentrant code. Reentrant code is, it is not changeable. Only thing which is changeable here is the data of the user. So 3 data is there. So what we do, we place these 3 data on 3 different frames, but the MS Word is kept only at one place, and all the tables, page tables of all the processes will be indicating to this particular frames. Like ED1 is frame number 3. So ED1 will be marked frame number 3 in all the process. Similarly, ED2 frame number 4, it is marked in all the processes, and ED3 in frame number 6, it is marked in all the process, this frame number 6 only. The data part is different. So for process P1, we have got the data part in frame number 1. For process 3, the data part is in frame number 2. And for the process P2, the data part is in the frame number 7. So this is how we can perform the sharing in our paging scheme. Thank you.